Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 22, VHDL Design, section or number 3. This lecture is the last lecture of chapter 4, titled Design with Standard Modules of the course Digital Logic Design, or Digital Electronics, or Digital Systems. The next slide is a disclaimer for you to read. I cite 3 references here for you, but there are a numerous number of references available in Digital Logic Design. We covered all the topics of Chapter 4 from decoders to FPGAs. Today we are going to talk about VHDL Design, which is the last lecture of Chapter 4. VHDL code for 2 to 4 decoder without an enable input. This is a very simple program. If you remember, a decoder will convert a binary input to 4 outputs, which they are the midterms of one of them will be active at a time. So if 0, 0, the inputs M0 will be generated. So because the decoder is a midterm generator, if the output active high, so we'll start with library IEEE, use IEEE standard logic 1164 that all entity DEC, which stands for decoder 2 to 4, is we define the input W in standard logic vector. We used here 1 down to 0, 1 down to 0, and we used F as the output, which is standard logic vector 0 to 3. So this is generate the midterms M0, M1, M2, and M3. And the entity name, which is DEC2, 2 to 4, then we have semicolon. Then the architecture statement, we will call the architecture behavioral of DEC2 to 4 is, we begin with W, we select. W is the input, because the input is changing. W is 2-bit input. It will be 1, 0, 0, 0, means M0 will be active when the input is 0, 0. It will be 0, 1, 0, 0, it means M1 will be active when 0, 1. It will be 0, 0, 1, 0 when 1, 0, the inputs, and 0, 0, 0, 1 when others. Okay, so this will give me the 2 to 4 decoder without an enable signal or input. I will end the behavioral, which is the name of the architecture. So the behavioral will be ended, and this will be the end program. Now, I would like to add an enable input. So this is the same entity modified. We change the name to DEC2 to 4 EN with enable. So I have W, again, is 2-bit input. We define it as a vector from 1 down to 0. We define an enable EN as a single bit, so this is input in standard logic. And F also is the vector, the output vector from 0 to 3, and this will be the midterm value. I will end the entity name, which is DEC2 to 4 EN, semicolon. Architecture behavioral of DEC2 to 4 EN is, I will define the signal enable standard logic vector 2 down to 0. So this signal is defined and enabled between the architecture before you begin. Once you begin, what's the enable? We defined it as a 3-bit. The enable is the concatenation of EN and W, so it will be a 3-bit. So I have the enabled bit. The enabled bit over time has to be 1 for the decoder to work, and W, which is the input, either 0, 0, 0, 1, 1, 0, and 1, 1. So when enable, E-N-A-B-L-E, when enable, this is the signal we defined, it's a 3-bit, select. I will assign F to be 1, 0, 0, 0 when I have 1, 0, 0. So this is midterm 0 has been generated. Midterm 1, 0, 1, 0, 0, when the enable 1, and the input W is 0, 1. And we'll have 0, 0, 1, 0 when the enable 1 and W 1, 0, the input is 1, 0. And it will be 0, 0, 0, 1 when the enable is 1 and the input is 1, 1. And will be all zeros when others. So here actually this is a better design for the decoder with enable signal, because the output will be all inactive if the input came in any form start with 0, because the enable then is inactive. So once it is 0, so we define this. When others, it means all the possibilities that occur where the enable signal is 0. The enable, which we mean by EN, or the enable ENABLE will be 0XX, in other words. So in behavioral, which is the name of the architecture, and this is another code for the 2 to 4 decoder with enable input. Now I would like to add a process. I would like to use a process with enable signal. So this is another form of the code. I will call it TC2 to 4 enable again. And port W, this is in standard logic, 1 down to 0. So I have a 2-bit input, 0, 0, 0, 1, 1, 0, and 1, 1. I have a single bit enable. And I have F is the output, which is the midterms from 0 as a standard logic vector from 0 to 3. I will end the entity name, architecture behavioral of DC2 to 4 enable is begin. Now the process elements are EN and W, because the process sensitive to those changes. Okay, so EN and W, I will begin if EN is 0, then all zeros will be assigned to F. Else, if W 0, 0, it means EN 1 now. If W 0, 0, then I will assign 0, 0, 1 to F. If 0, 1, if W 0, 1, I will assign 0, 0, 1, 0 to F. If W is 1, 0, then I will assign 0, 1, 0, 0 to F. Else F will be assigned to 1, 0, 0, 0. So clearly, one term will be active at a time. One term will be active at a time from M0 to M1, M0 to M1. And here we assigned M0 to be the least significant bit. So M0, if we look at the block diagram, is the lower output of the output at the bottom. And M1, which is M3, will be the output at the top. Okay, and if in the process, we can change this by manipulating the values of F by reversing the value if we wish to. In the process, once we do the process, because the process within the architecture statement in behavioral, which is the end of the program, we end the architecture. The next slide talk about an encoder, 4 to 2 encoder. And this code is very simple as well. Library, and they use IEEE standard library. Those are common. Entity priority encoder is port. Define the input as I input standard logic vector 3 down to 0. So we have 4-bit input. Y is the output, is a 2-bit output, standard logic vector 1 down to 0. And G is the active indicator, active output indicator, or correct output indicator, the out in standard logic. So in 1 bit, I will end the entity name, which is a priority encoder, architecture behavioral or priority encoder of the entity name priority is begin with I select. I will assign W to be 0, 0 when I have 0, 0, 0, 1. So this is indication that if I have minterm M0 is active at the input, okay, so 0, 0, 0, 1, the Y will be assigned 0, 0, okay. Now, when I have 0, 0, 1, 0, I will assign Y to 0, 1. 0, 0, 1, 1, I will assign 0, 1. 0, 1, 0, 0. I will assign y to 1, 0. Then 1, 0, 0, 1. I will assign 1, 0. So 0, 1, 1, 0, I will assign 1, 0. 0, 1, 1, 1, I will assign 1, 0. When others, I will assign 1, 1. So by doing this, I establish priority encoder to allow me to serve, to acknowledge which line input is active, and the output will be active accordingly. Now, with I select G to be 0 when 0, 0, 0. If all the outputs are zeros, none of them is active, okay, and G will be 1 when others. So this is I have an active output or a real output, because G will be 1. Then I will end the behavioral, which is the architecture name, and by this the program will be ended. You can compile it and test it on a chip or any programmable logic device if you wish to, or just simulate the program to see how it is working. Now, this is the alternative code for a 41 encoder. Again, here we defined I, we define Y as a vector, 2-bit vector, the input. I is the input, Y is the output. The input is a 4-bit vector, and G is the output as a single bit, so it's defined as standard logic, and it priority encoder. Architecture behavioral or priority encoder is begin. I will assign Y be 1, 1 when I3 is 1. So if the most significant bit of I is 1, I will assign Y to be 1, 1. I will assign to 1, 0 when I2 is 1, else I will assign 0, 1 when I1 is 1, else I will assign Y0. So again, this will be a priority encoder to 1 encoder. B will be 0 when I will be 0, 0, 0, 0. When the input will 0, else will be 1. Else will be 1, behavioral. So G again easily could be defined, and this will be a priority encoder with output G. Now, if we can add a process, we can do that here. The process, entity has not been changed at all. We have I, Y, and G. I and Y defined as vectors, and G as a single bit. I will end the priority encoder, architecture behavior of priority encoder begin. Process I, because I is changing. I is the input. Begin. If I3 is 1, I will assign Y to be 1, 1. Else, if I2 is 1, then Y will be 0. Else, if 1 is 1, then Y will be 0, 1. Else, Y will be 0, 0, and in the process again, I will assign G to be 0 when the input I is 0, 0, 0. It's very true. Else G will be 1. Else will be G1. So G1 indicate an active input, an active output, and I will end the behavioral, which is the name of the architecture. And by this, I use a process to design a 4-to-1 priority encoder. Of course, you can expand this easily by changing the vector to any other size encoder if you want to. Let's do design 4-to-1 multiplexer. Multiplexer, we have 4 input and 1 output as a switch. So the entity will be port D0, D1, D2, D3 input standard logic. S the select line will be a 2-bit vector from 1 down to 0, and F is the output function. So architecture behavioral of max 4-to-1 is begin with S select. F will be, I will assign D0 to F when select line is 0, 0. D1 when 0, 1. D2 when 1, 0. And D3 when others. Very easy. In behavioral. I can package this program. Okay. To package it, it means this will allow me to use it in hierarchy in other programs. Okay. If I can call it anytime. Once I package it, I can call it anytime and reuse it without writing it again. So it will be in my memory on my computer. So the package code library IEEE use IEEE standard logic 64.0 package multiplexer 41 underscore package is component multiplexer 41. This is actually came from the definition of the entity D0, D1, D2, the N, standard logic, S and F, end component, end the package. I will compile it and I can use the entity name MUX421 anytime once you package it. For instance, I would like to build 16:1 multiplexer using 5 MUX421. We've done this in another lecture with expansion, multiplexer expansion. Please refer to it. I do have block diagram, and I refer to this block diagram to design this, a 16:1 multiplexer. So since I have a package, I will use work.mux421 underscore package dot to link the package to this program. Entity MUX16:1, I will define it. I have D, the input. Here I have the D's will be 0 to 15, and I have the select line. I have a 4-bit select line, so it's 3 down to 0, and I have a single bit output, so it's in standard logic. I will end MUX16:1. Architecture structure of MUX16:1 is I will define signal. This is the output F0, F1, F2, F3 multiplexer, the first 4 multiplexers. Then those output will be fed basically to the last multiplexer where we are picking up the corresponding signal. Okay, so we do this. So I will define this F signal F0, F1, F2, F3. We have to define them. We'll get an error because we are going to use them. So they are not defined because they are not output, they are not input, so we don't define them in the port statement, but they have to be defined in the architecture statement. So signal F0, F1, F2, F3 in standard logic. Again, now the multiplexer 1, we have D0, D1, D2, D3, and the select signal 1 down to 0, 2 bits. Those are the least significant bit. And the output will be F0. The same thing with multiplexer 2. The output will be F1. The same thing with multiplexer. The output will be F2 and F3. Now those 3 outputs will be fed as inputs to the last multiplexer. So I have F0, F1, F2, F3. And with the select bit is the most significant bit, which is S3 and S2. And the output will be F. F is a real output defined in the entity as an output bit in structure, and this will be a complete program 16:1 multiplexer using 4:1 multiplexer and utilize the package, and this is called a hierarchical code because this is a higher hierarchy than the MUX421. We can use the 16:1 if we package this. We can package this, and we can use it in another program. Okay, don't forget, if you do actually packaging, always you must link it by the use work library, and you have to define the package here. Now, this is a 1 to 4 demultiplexer, which is the opposite of a multiplexer. The input will be the select line, the input demultiplexer, which is a vector 1 down to 0. We have the input data in a single line, which is in standard logic, and F, which is an output in the standard logic vector 0 to 3. So we have 1 to 4. So F will be a 4-bit output. I will end the demultiplexer. Architecture behavioral of demultiplexer is begin process. The sensitive data in the process are the input, which is input data, and the select line, which is S. Begin, if input data is 0, then F will be assigned with 0, 0, 0, 0. Else, if the select line 0, 0, then F will be 0, 0, 0, 1. Okay? So the least significant bit of F will become 1. It means the data will go to the least significant bit of f. If s is 0, 1, then f will be 0, 0, 1, 0. Okay. If s is 1, 0, then f will be 0, 1, 0, 0. Else will be 1, 0, 0, 0. When we say else, it means then the s will be 1, 1, and the select input is the input data as 1. Because when the input data is 0, the f will be always 0, 0, 0. I have to end if, I have to if the statement, end if, end the process, and in behavioral, which is the architecture, and this will be a complete code for Demultiplexer using a process statement. This will be the last, actually, lecture of chapter 4. I would like to thank you so much. Please subscribe. Hopefully to see you very soon. Sincerely, Dr. Hassan.